Hello, I'm Dimitri from CNES, and today I want to introduce Bulldozer, a free open source scalable software for DTM extraction. So just a little reminder, a definition. So DSM is a surface seen by the satellite or aerial. DTM is what we are trying to reach, is ground basically, and using those two information we can compute the digital elevation, digital heights model, DTM, which allow us to retrieve the elevation for example, buildings or trees. So why we are working on this? It's because there is more and more large-scale 3D mission, like CO3D. It's a satellite mission that will be launched in 2024. It should be, at least. Or maybe also LiDAR HD. It's a IGN mission that tries to map all the France territory with a LiDAR. And you also have a previous mission like Pleiad or Pleiad Neo, and those missions allow us to compute DSM through satellites using photogrammetry. About the usage, we can list some of it. So, for example, all the topography or hydrography, for example, like predict the water level and the impact of on the population, bathymetry for working on all the coastal areas, 3D urban reconstruction. Using the digital height model, we can compute the height of the building, so we can make a 3D map of city, like digital twins or stuff like that. There is also, it can also help us to distinguish, for example, low vegetation or high vegetation for a land cover map. And there is also some military needs. I don't work on that, so I cannot really give you some details about that, but we know that it can be helpful. Here it's an example of a project on which Bulldozer is used. It's AI for geo, so we are working on load 0 is a footprint basically. We compute the load 1, and after that we can make like a 3D reconstruction of a city. Here on the left side you have like a Bulldozer on which we put just the building with load 1, and here you have like the output DSM through photogrammetry. So you see that there is a lot of noises in the street, or for example you can see here, this is a river, and the elevation is completely, not well estimated. And on this project, we also produce a land cover map. So here you have an example where the 3D information is used as a feature for the neural networks. So for DTM extraction methods, I would say there is mainly two ways of computing it. You can do it using exogenous data, like above ground mask, like you provide a mask where you map every building, every trees or stuff like that, and you indicate to the algorithms where you have to interpolate the DTM. Or you also have time to time to provide the water mask or no data mask, indicating where, for example, the satellite had occlusions that produce no data in the 3D model. Or you can work without exogenous data, and mainly it's based on closed simulation methods. So I will introduce you those kind of methods because Bulldozer is derived from those kind of approach. So basically what you're trying to do is you take the DSM, you invert it, you simulate it close or a sheet, and you make it fall on the DSM, and after that, by inverting it again, you will retrieve the DTM. So how it works a little bit in detail. So here you have a representation of like DSM in black, and as you see, it's like kind of building, but it's inverted. So this is the roof of our building, and the ground is on the sides. The particle represents the close. First of all, we will make a gravity step. So we will make like the fall. We will simulate the fall of the sheet without taking into account the DSM. After that, we will make an intersection check for checking if the DSM is under if the DTM is under the DSM. And in this case, we put the particle of the cloth on on the DSM, because we don't want that our ground end up to the DSM. And after that, we apply the tension on the remaining mobile particles to be able to well estimate the elevation for the ground. So for the tension, you have like two possibilities. The first one is when you have two neighbors' mobile particle. In this case, both of them will interact with the other. And in the other case, you will have like a fixed particle, like a particle that stick on the DSM that will impact the other one, but it will not be impact. The value of the tension will provide a different kind of result, and you will have different impact on the final sheet. And so for the tension, you have a trade-off to do, basically, for those kind of method. If you put a high tension, you will well retrieve the elevation for the building, because you will quite well estimated the ground elevation, but you will have like we call unhook. You will unhook the landscape for like how to say that, like hilly areas. So in the other end, if you reduce the tension, you will well reconstruct the 3D of those areas, but in the other end, you will reduce your quality of the DTM on urban areas. So yeah, this is something that we try to tackle in Bulldozer, but I will explain it later. And for those, in those field of closed simulation, there is also multi-scale computation methods, and Bulldozer is one of them. So basically what you're trying to do is you're starting with your DSM at a very high resolution, like for example, we're mainly working on a Pleiad DSM at CNES, so it's a 50 centimeter resolution DSM. And after that, we're making downsampling, and we do it until reaching a certain point, like a low-resolution DSM. At this point, we will simulate the close as I presented before. So we start with like a flat sheet, and after that, we make the simulation of the fall. We will retrieve a first version of the DTM. So quite very poor quality, but quite easy to compute since it's on a very little, like with very few pixels. After that, we will upsample the DTM and the DSM, and we will do it again. So we will recompute the DSM at this resolution, but instead of starting with a flat sheet, we will use the close we simulate at the previous step. So basically, you already have a kind of shape of the landscape, but here you're trying to improve the quality on adding more points through your DSM, and you repeat this action until reaching your output or your input DSM resolution. So that allows you to really fastest your process and improve the computational performances. And just like a little explanation on how it works really under the, how we perform the simulation. This is a simplified version, but you can understand easily with this. So first of all, we have our gravity step. So one gravity step is just adding, like you have a MNT at a certain level in the pyramid, and you just making an addition of the elevation, so just plus on all the pixels. After that, you will make the minimum between MNS and DSM and DTM. Sorry, it's French. I forgot to translate it. So yeah, DTM, DSM. So when you compute the minus, you will find the intersection between both of them. And after that, to applying the tension, you make an uniform filter, and after that, you will produce like a tension. And this is like a full gravity step. At each step, you will apply a certain number and inner time the tension. And when you finish all this process, you have a DTM at the level of your pyramid, and this will be the input for the next level of the pyramid. Okay, so here is the representation. So you see the resolution. You see that we're starting to retrieving the landscape, I would say. But you have some here and here, some default, and I will explain what's this. But basically, you see, for example, at the beginning, we're not able to retrieve this area, but by making the process more and more, we are able to really fit on the groundscape shape. Sorry. So the main limit of the drop close methods is that there is no data handling. So basically, when you're working on satellite imagery, you have a lot of no data on your DSM because you have occlusion. You can have like the satellite cannot see everything, so you have no data. And in a lot of methods, it's not well taking into account. The drop close methods in open source are mainly used for LiDAR missions. So basically, it's very I would say beautiful DSM compared to satellite, because I will show you later, but the satellite's DSM can have a lot of noise in it, and we have to be able to tackle those kind of DSM. There is no landscape adaptation. Basically, they always start with like a flat sheet, and after that you have like the tension is not adaptive to the scene, so it can be problematic. They didn't take in account like the input DSM information, like metadata, like the resolution. The method is the same if you run it on a LiDAR or on a satellite, but in our case we try to adapt on those kind of taking in account the size of the scene and also like the sensor. There is an issue with scalability and stability. In the method we found, there was no tiling method or stuff like that, so it was quite long when you were trying to run it for a big scene. For example, on satellites, we mainly work on 20,000 by 20,000 DSM scene, so it can be very problematic for the computer performance. And so basically just explained that the performance was not enough for us. And time to time also the close had a significant underestimation on the hill, like it didn't stick and follow the landscape because it stick to the two sides of the hill, and since we didn't apply enough gravity step, we really underestimate the DTM, sorry. And you can see here another example. I told you about the noise in the DSM. You saw it previously on the video. But for like here it's water, or here it's like a homogeneous area. And when you computing a DSM through photogrammetry, those uniform area end up in a very noisy data because there is a bad estimation of the elevation. And so those areas are very how to say that difficult for the method, because like the cloth will stick to those areas and will not be able to really follow the landscape. So that's why we developed at CNES our own software, so Bulldozer. Our goal was to be able to perform on large-scale DTM. Like I told you, there is a lot of mission incoming, and we want to be able to manage this kind of data. We wanted to work without exogenous data, since I told you we need other method required like water mask or stuff like that. Since we're trying to work on everything everywhere on Earth, like if you have a segmentation model for a building, it may work for like Europe, but if you use it on I don't know, in Africa, maybe the performance will really drop-off, and it's end up in like a bad input mask, and it will be problematic for your method. So we want it to be completely based on only the DSM, the input DSM. We wanted to work for both photogrammetric and LiDAR DSM, so work with very high resolution DSM as for like I said, satellites DSM. We wanted to perform on noisy DSM. So here is an example. You see, so it's not very well restituted, but anyway, this is like a part of Toulouse in like our city. And here is it's a river, and you will see that on the elevation, when you see it, it's here. You see it's very noisy. Like there is a lot of variation on the elevation, and it's just due to the photogrammetry. We want it to be very scalable, since we want to work on very large scale DTM, but we want to do it quickly. And our goal was to outperform or at least equalize existing methods and to be adaptive to the hardware resources to really optimize the memory and CPU usage, basically. And even if we want it to be quite performance, oh, okay, I don't have at all the same times. Okay, sorry, I will speed up. So yeah, we want it to be easily to access through a Python API. So even if our core code is in Python or C++, we wrap it in a method to be easily accessible. Okay, so since I don't have a lot of time, I think I will be quite quickly. First of all, I will explain very quickly the Bulldozer pipeline. So basically, since we don't have exogenous data and just DSM, we have to detect the no data, and we distinguish two types of no data. Like the border no data, so the area we don't want to interpolate, and the inner no data, like the no data that come from occlusion, or for LiDAR, like no signal. And to do that, in this case, we want to really compute the DSM on all these parts. So this is not so simple to distinguish without information where is the limit, because even here, if the no data of the layer touch the border no data, we wanted to distinguish both of them. After that, we wanted to be able to detect and preprocess the disturbed area. Like I told you, the water is very difficult and impacts the method. So we were able to compute a mask. And you can compute this mask without running all the function if you want just to detect a disturbed area in a DSM. And after that, we fill it using a recursive IDW method. So it's inverse distant weighting. Sorry, I don't have the time to explain it. And after that, we have a clean preprocessed DSM to the drop close method. For the drop close method, we produce a quality mask where we store all the information about where we make the interpolation and where we stick to the DSM. We were able to handle noisy DSM, and we also adapt to the landscape, basically to be able to fit to hilly areas. We tried to remove all the magic numbers of the methods and transfer it to concrete parameters. So instead of like I will apply 100 times an inner, we're trying to, based on the landscape and the scene, we're trying to determine the number of iterations of each step. But we still want to be stable, meaning that we guarantee like a convergence, and even in a very various landscape, you are sure that the Bulldozer will converge, even if it will not do as he compute at the beginning the number of steps. Like we have a margin to ensure the computational time. And we also mainly work on the scalability, so we basically multiprocess and adapt everything in C++ to improve the running time. For the post-processing, basically, since our mask is not perfect for distinguish the disturbed area, we still have some points that were considered with a valid elevation. It will end up in the end with pits, so the cloth will stick to those points. So we had something to like a little bit smooth those areas. And here you have an example. So there is still some scars on the DTM, but we are working on it. And for the elevation, in this case, it's just some centimeters. So it's visible with ill-shade vision of QGIS, but for the computational, for the performance, when we compare to like a reference, it's okay. So here's just a little comparison between Bulldozer, so it's here in orange, and like DrapCloth. You see that we are not, we follow the landscape, but we still keep the information of the above ground, like trees and houses. And you see that the disturbed area does not affect the Bulldozer DTM. Here it is. I will skip the animation. And yeah, we worked on the accessibility. So we try to make it simple to use. So basically, you create your own virtual environment with Python. And after that, you have two possibilities. You just pip install it, or you can clone the repository and make the install by your own. For the usage, you have two methods. So you can use a Python API or use a command line interface. For the command line interface, you just provide a configuration file where you indicate the path to your input DSM and the output directory. You can also provide some other parameters. And for the Python, it's the same. You can provide the configuration file, or you can provide the parameters directly in the function. I will skip on the usage, but basically this is only two required parameters, so input DSM and output directory. After that, you can provide other parameters, like if you want a DHM or if you want to change the resolution. When you change the resolution, it's not simply that we reproject the DSM at the end at the resolution you ask. Is that we will determine when we have to stop in the pyramid, and will not make all the computation until reaching the very high resolution to recompute the low resolution. We just stop at the corresponding level. And you can, for example, indicate the number of core on your CPU that can be used. After that, you have more advanced settings, like the max object size, the size I told you that determine the tension we will apply. And after that, okay. After that, you have like core settings that I don't suggest you to touch. If you want to touch those parameters, I suggest you to contact us or to really dive into the code, because it can be quite difficult to understand. So here is so here is the current state of Bulldozer. So you see the Toulouse DSM and our DTM. What we want to the upcoming works. So basically, we want to work on the external stability. So as I said, there is a CO3D mission that will cover all the world, and the DSM will be tiled. So we want to be able, by computing a DSM, to, if we had new information, to keep like a kind of stability in the result, because currently Bulldozer is stable from an internal point of view, meaning that if you how to say that? Regardless of the number of CPU you will use and the multiprocessing you will perform, it will be always the same result. But here it's also to be like to have margin stability produced with the DTM to be able to fit tiled DTM. We will mainly work on the coastal digital twin, so work on the 3D reconstruction for all the coastal areas. We will publish the test and full documentation soon in the next version of the tool. It's a very young tool, so we are still developing a lot in it. And yeah, as I said, we have some disturbed area detection improvement to do, and also some pits detection. Yeah, we developed QGIS plugin, so you have like a modular and where you can use it. And if we just have to publish it because it's already available, but yeah, we didn't really put link and everything. So very soon, I think in some weeks or stuff like that, we will put the link directly in the repository. So yeah, that's it. Thanks.